Hello, everyone, and welcome back. If you're new here, then we're doing NCRT and actually every line of it in the easiest possible way. So, without further ado, let's just get started. And today we'll be discussing the solid state from class 12, physical chemistry. So, let's begin. We are mostly surrounded by solids and we use them more often than liquids and gases. For different applications, we use solids with widely different properties. These properties depend upon the nature of constituent particles and the binding forces operating between them. Therefore, study of the structure of solids is important. The correlation between structure and properties helps in discovering new solid materials with desired properties like high temperature, superconductors, magnetic materials, biodegradable polymers for packaging, biocompliant solids for surgical implants, etc. So, like always, the NCRT is trying to give us a sort of an intro about the solids, how we use them every day, and how they're really important for us, and what binds them together, the forces that actually make them the solids. Fine, and then the relation between their the structure and the properties, so that we can actually discover new solid materials and see what all suits us towards development. So moving on, we have from our earlier studies, we know that liquids and gases are called fluids because, of course, of their ability to flow. The fluidity in both these states is due to the fact that the molecules are free to move about. So, what differs, how, in what way do the solids differ from the fluids? Is that the fluids, of course, can freely flow. That's why we call them the fluids, and the solids cannot flow. And that is obviously because at the molecular level, they're free to move about. On the contrary, the constituent particles in solids have fixed positions. This is something we already know and can only oscillate about their mean positions. This explains the rigidity in solids. So, in crystalline solids, the constituent particles are arranged in regular patterns. So, we always hear of the term crystalline. Crystalline, it basically means something that has been put together in a certain pattern, in a regular pattern. Right? And about the motion of the particles, about how randomly they're able to flow, we know it already. We've been doing it since class 5 or 6 in the physical properties of matter. So they're trying to explain a similar thing over here. The way solids are rigid, you cannot actually make them flow. They're not, the molecules are tightly packed and everything. The intermolecular spaces are really strong. The spaces are big, but they're really weak, the forces in case of the fluids, but in case of the solids, intermolecular forces are really strong. In this unit, we shall discuss different possible arrangements of particles resulting in several types of structures, the correlation between the nature of interactions within the constituent particles, and several properties of solids will also be explored. How these properties get modified due to the structural imperfections or by the presence of impurities in minute amounts would also be discussed. So, basically, what all we'll be discussing in this lesson will be what are the various ways you can actually arrange the solids, the particles in the solids, what are the molecular forces, what are the ways they're put together, what if there are impurities in the solids. That's what all this lesson's really easy. I think physical chemistry has to be easy every time we do it. So in class 11 you've learned that matter can exist in three states, namely the solid, liquid, gas. I think we've been doing this since class 2 maybe. Under a given set of conditions of temperature and pressure, which of these would be the most stable state of a given substance depends upon the net effect of two opposing factors. So we have two opposing factors. We have the intermolecular forces, which will keep the molecules closer. Fine. Molecules would refer to atoms or ions. We'll be discussing that later on. Whereas thermal energy tends to keep them apart by making them move faster. So what basically makes it, we always say gases have large intermolecular spaces and they can randomly move about. But what makes them move about is this thermal energy, the kinetic energy associated with the molecules that will help them just move away, randomly spread out. But the intermolecular forces will keep the molecules tight. So these are two opposing forces, and we'll see what force will overrule the other, and we'll see what type of physical state we are getting out of it. At sufficiently low temperature, the thermal energy is low. So thermal energy would be directly proportional to temperature, of course. Thermal hai, so obviously it will depend upon temperature. And intermolecular forces bring them so close that they cling to one another and occupy fixed positions. These can still oscillate about their mean positions, and the substance exists in solid state. The following are the characteristic properties of the solid state. They have definite mass, volume, and shape. Intermolecular distances are short. Spaces nahi hai beech mein because particles are very close. Intermolecular forces are strong. The constituent particles, whatever it is, have fixed positions and they can only oscillate about their mean positions, and they're incompressible and rigid. We know it already. Then coming to amorphous and crystalline, these also we might have heard. Let's come to the depth of it today. Solids can be classified as crystalline or amorphous on the basis of the nature of order present in the arrangement of their constituent particles. So मतलब कोई certain arrangements या randomly रखे हुए amorphous is solid या crystalline. A crystalline solid usually consists of a large number of small crystals, each of them having a definite characteristic geometrical shape. So, in a certain pattern, you will have in a crystalline solid the molecules. In a crystal, the arrangement of constituent particles is ordered. It has long range order, which means that there's a regular pattern of arrangement of particles which repeats itself periodically over the entire crystal. So, what do you mean by long range order? यानी बहुत repetitive units तक periodic repetition होगा of the regular pattern of arrangement of particles in a crystalline solid. Sodium chloride, for example, and quartz are typical examples of crystalline solids. An amorphous solid. Amorphous means no form, Greek में. कोई form ही नहीं है. Consists of particles of irregular shape. Fine. The arrangement of constituent particles is such a solid is only short range order. Fine. Arrangement बहुत short range है. Periodically repetitions नहीं हो रहे. In such an arrangement, a regular and periodically repeating pattern is observed over short distances only, which eventually makes it amorphous. Such portions are scattered, and in between the arrangement is disordered. Fine. The structures of quartz crystalline and quartz glass, fine, quartz glass is amorphous, are shown. You can see this is quartz, really ordered. This is something like quartz glass, and they say that it is amorphous. Fine, हम दूर से भी बता सकते हैं molecular arrangement जो है, though there might be repetitions, but they're short order. Fine. While the two structures are almost identical, yet in the case of amorphous quartz glass, there's no long range order. Fine. The structure of amorphous solids is similar to that of liquids. Glass, rubber, plastics are typical examples of amorphous solids. You need to remember the examples. Fine. Due to the differences in the arrangement of the constituent particles, the two types of solids differ in their properties. Obviously, अगर arrangement ही particles का different है, तो properties भी differ होंगी. Fine, like we see genotype change होगा तो phenotype change होगा. What we do in bio. Next, crystalline solids have a sharp melting point. On the other hand, amorphous solids often soften over a range of temperature and can be molded and blown into various shapes. So, एक particular fixed melting point भी नहीं होता amorphous solids का, fine. Over a range of temperature, you can mold them, you can convert them into shapes because they don't have a proper structure. On heating, they become crystalline at some temperature. Fine. These amorphous solids, हम उनको crystalline बना सकते हैं. Some glass from ancient civilizations are found to become milky in appearance because of some crystallization. Fine. Like liquids, amorphous solids have a tendency to flow, though very slowly, because we are saying amorphous solids और हम fluids या liquids और gases को आपस में compare करते हैं. Therefore, sometimes these are called pseudo solids or super cooled liquids. ठीक है? These are both names of amorphous solids. Pseudo solid मतलब truly वो solid नहीं है, truly उनका कोई crystalline structure नहीं है, और super cool liquid मतलब इतना cool किया liquid को, thermal temperature, thermal energy itna kam laya that they were now next to liquids. Glass panes are fixed windows or doors of old buildings are invariably found to be slightly thicker at the bottom than at the top. This is because of the glass flows down very slowly and makes the bottom portion slightly thicker. It might not be so visible clearly, but you should have it in mind somewhere down the line that थोड़ा सा flow होता है because glass is being amorphous solid has tendency to flow because it will mimic what? It's a super cool liquid, right? It's a pseudo solid. It'll try to mimic the liquid and it'll try to flow. The bottom wala will be slightly thicker. Crystalline solids are anisotropic in nature, that is, some of their physical properties like electrical resistance or refractive index show different values when measured along different directions in the same. You might have done this in physics also. Anisotropic मतलब जिसको different direction से measure करो तो different value आएगा. This arises. अब ये क्या कह रहे हैं? Crystalline है anisotropic. This arises from different arrangement of particles in different directions. See, since the arrangement of particles is different along different directions, the value of same physical property is found to be different along each direction. Amorphous solids, on the other hand, are isotropic in nature. You have to remember, amorphous ही isotropic हो गए. There is no long range order in them और arrangement irregular है along all the directions. There is no regularity. तो कोई यहाँ पे issue ही नहीं है कि हम किस direction से जाएं. There is no direction, there is no regularity. Fine. Therefore, value of any physical property would be the same along any direction. Now, there is this table given. Shape में definite shape, irregular shape. Melting point, melt at a sharp point, gradually soften over a range of temperatures. Similarly, cleavage property. Sharp edge tool, they split into two pieces and the newly generated surfaces are plain and smooth. When they are cupped, what happens? They're irregular surfaces. Of course, because irregular था तो eventually irregular pieces में cut होगा. Heat of fusion, definite heat of fusion. कोई definite heat of fusion नहीं है. Anisotropic है, isotropic. true solids, pseudo solids, long range order, short range order. ठीक? Next. Amorphous solids are useful materials. ग्लास रबर, हमने अभी जब ग्लास देखा तो हमें ऑलरेडी पता चल गया कि ग्लास हमारे लिए बहुत इंपॉर्टेंट है. हाँ, रबर, plastics find many applications in our daily lives. Amorphous silicon, ठीक, is one of the best photovoltaic material available for conversion of sunlight into electricity. ठीक, amorphous silicon ही वो चीज है जो आपको याद रखना है. ये एक photovoltaic material है. Moving on to classification of crystalline solids. We have learned about amorphous substances and that they have only short range order. However, most of the solid substances are crystalline in nature. For example, all the metallic elements like iron, copper, silver, um, non-metallic elements like sulfur, phosphorus, and iodine compounds like sodium chloride, zinc sulfide, and naphthalene form crystalline solids. ठीक है, mostly हम क्या देखते हैं? Crystalline solids. Crystalline solids can be classified on the basis of nature of intermolecular forces operating in them into four categories. That is molecular, ionic, metallic and covalent solids. Of course ये हमने इससे पहले भी किया है. जो crystalline solids है उनकी nature of intermolecular forces पे हम उनको classify करते हैं. Molecular है, ionic है, solid हमारा metallic है या covalent है. Fine. Now let's just come to the categories. The first one is molecular solid. Molecules are the constituent particles of molecular solids. Self-explanatory hai. These are further subdivided into following categories. You have non-polar, you have polar, you have hydrogen bonded. ठीक. तो non-polar में क्या होगा? They comprise of either atoms, for example, argon and helium, or the molecules formed by non-polar covalent bonds, for example, H2, Cl2, and I2. Molecular solids. अब हमें ये तो समझ में आ गया कि मॉलिक्यूलर सॉलिड में मॉलिक्यूल्स ही सॉलिड बनाएंगे, बट वो कैसे मॉलिक्यूल्स होंगे? वो नॉन पोलर होंगे, यानी जो बॉन्ड्स बनेंगे वो पोलैरिटी नहीं देखेंगे. देयर विल बी नो डाइपोल मोमेंट. फाइन. द एटम्स और मॉलिक्यूल्स आर हेल्ड बाय वीक डिस्पर्शन फोर्सेस और लंडन फोर्सेस अबाउट व्हिच यू हैव लर्नड. दीस सॉलिड्स आर सॉफ्ट एंड नॉन कंडक्टर्स ऑफ इलेक्ट्रिसिटी. नॉन कंडक्टर्स होते हैं, सॉफ्ट होते हैं, दे हैव लो मेल्टिंग पॉइंट्स ऑब्वियसली जब सॉफ्ट है, एंड आर यूजुअली इन लिक्विड और गैस स्टेट एट रूम टेम्परेचर एंड प्रेशर. दिस इज अबाउट योर नॉन पोलर मॉलिक्यूलर सॉलिड्स. अब पोलर में क्या है? पोलैरिटी आ रही है. मॉलिक्यूल्स ही हैं, अभी भी सॉलिड मॉलिक्यूल का ही बना है, बट देयर इज इलेक्ट्रोनेगेटिविटी डिफरेंस. द बॉन्ड्स आर पोलर, देयर इज सम नेट डाइपोल मोमेंट. सो वो ये कह रहा है द मॉलिक्यूल्स ऑफ सब्सटेंसेस लाइक HCl, SO2, etc. formed by polar covalent bonds. The molecules in such solids are held together by relatively stronger dipole-dipole interactions. Fine. These solids are soft and non-conductors of electricity. They अब क्योंकि हम molecular forces कर रहे हैं तो हम यहाँ पे ionic bond वगैरह नहीं देख रहे हैं. हम क्या देख रहे हैं? बेसिकली हम we are discussing about the intermolecular interactions. Fine. तो वो या तो in non-polar molecular solids they were dispersion forces or London forces, and in case of polar molecular solids now they are stronger dipole-dipole interactions. Then again, soft non-conductors of electricity, melting point higher than those of non-polar, yet most of these are gases or liquids under room temperature and pressure. Solid SO2 and solid NH3 are some examples of such solids. अब hydrogen bonded में क्या होगा? Very easy. Intermolecular forces क्या होंगे? Molecular solids में the molecules of such solids contain polar covalent bonds between H, F, O or N atoms. ठीक. और किसके साथ? इफ हाइड्रोजन यू फाइंड विद एनी इलेक्ट्रोनेगेटिव एटम, वहां पे आप देखते हैं क्या? देयर इज पोलैरिटी, देयर इज पॉसिबिलिटी ऑफ हाइड्रोजन बॉन्डिंग. स्ट्रॉन्ग हाइड्रोजन बॉन्डिंग अकर्स binds molecules of such solids like H2O. जैसे आइस में लेते हैं, अभी आप बोलेंगे what is a liquid, but they've taken ice, fine, it's a solid, so there you will have hydrogen bonding. They're non-conductors of electricity again. Generally they're volatile liquids or soft liquids under room temperature and pressure. Coming to now ionic solids. Molecules हो गए, अब हम देखेंगे ionic solids. So in this case, ions will be the constituents of the solid. So ions are the constituent particles of ionic solids. Such solids are formed by the three-dimensional arrangement of cation and anion. Obviously, ions लेने हैं, तो positive or negative, bound by strong coulombic or electrostatic forces. हमें पता है electrostatic forces ही strong होते हैं सबसे ज़्यादा. These solids are hard and brittle in nature. They have high melting and boiling points. Since the ions are not free to move about, they're electrical insulators in the solid state. लेकिन molten state में they or else when you dissolve them in water, ions will become free to move about and they conduct electricity. Again the same thing, ions है लेकिन since solid state में है तो electrically insulators होंगे. Why? Because the ions even will not be free to move. But फिर हम उसको melt कर देंगे या water में dissolve करेंगे. Consequently, they'll start to conduct. Metallic solids. Again, metals are orderly. collection of positive ions surrounded by and held together by a sea of free electrons, है ना? मेटल कर्नेल होता है, बीच में उसके इर्द गिर्द हमारे इलेक्ट्रॉन्स होते हैं। तो ऐसा हमारे पास मेटलिक सॉलिड एक बनता है। मेटल क्या होता है? बेसिकली कलेक्शन ऑफ पॉजिटिव आयंस सराउंडेड by and held together by a sea of free electrons. These electrons are mobile and are evenly spread out throughout the crystal. Each metal atom contributes one or more electron towards this sea of mobile electrons. These free and mobile electrons are responsible for high electrical and thermal conductivity of metal. So metallic solids, अभी तक हमने देखा सिर्फ metallic solids ही conduct कर रहे हैं normal state में. When an electric field is applied, these electrons flow through the network of positive ions. हम conventional basis पे लेते हैं positive ions flow करें. Similarly, when heat is supplied to one portion of a metal, thermal energy is uniformly spread throughout by free electrons. Another important characteristic of metal is their luster and color. And in certain cases, this is also due to the presence of free electrons in them. Metals are highly malleable and ductile. We know drawn into sheets and drawn into wires. ये सब properties metals के ही होते हैं. और metals होते क्या basically? Positive ions or surrounded by sea of free electrons. Next, कोवलेंट और नेटवर्क सॉलिड्स. अब कोवलेंट सॉलिड्स कोई नेटवर्क सॉलिड्स यहाँ पे बोला है, अ वाइड वैरायटी ऑफ क्रिस्टलाइन सॉलिड्स of non-metals result from the formation of covalent bonds between adjacent atoms throughout the crystal. ठीक है? अब atoms के बीच में क्या है यहाँ पे? These are all covalent bonds. They are also called giant molecules. Covalent bonds are strong and directional in nature. Therefore, atoms are held very strongly at their positions. Such solids are very hard and brittle. Again, they have extremely high melting points and may even decompose before melting. They're insulators and do not conduct electricity. ठीक है? Diamond and silicon carbide are typical examples of such solids. ऐसे solids जहाँ basically जो हमारा crystalline solid है वो बना कहाँ से है? नॉन मेटल से. ठीक है? और जब नॉन मेटल्स के बीच में बॉन्ड बनता है वो किसका बनता है? कोवलेंट बॉन्ड बनता है. फाइन. और कोवलेंट बॉन्ड से अगेन इट्स अ स्ट्रॉन्ग बॉन्ड, इट्स डायरेक्शनल इन नेचर. अगेन देयर इंसुलेटर्स. यहाँ पे डायमंड एंड सिलिकॉन कार्बाइड आर गिवन एज द एग्जांपल्स. ठीक. Graphite is soft again and a conductor of electricity. Its exceptional properties are due to its typical structure. अब graphite भी यही है basically carbon carbon carbon, but हम देखेंगे यहाँ पे कि इसके कुछ special properties है. Carbon atoms are arranged in different layers and each atom is covalently bonded to three of its neighboring atoms in the same layer. तो carbon का tetravalent होता है, तीन neighboring atoms से graphite में surrounded है, तो एक electron, fourth valence electron of each atom is present between different layers and is free to move about. These free electrons make graphite a good conductor of electricity. Different layers can slide over the other because layered structure that you can see it's beautifully depicted over here. These are the layers and you can see these bonds between the layers. This makes it soft and a good lubricant because the layers can slip over each other. Different properties of four types of solids are discussed. अब ये वही है, उसको इन्हें थोड़ा tabular form में दिया है. You can have, so we have again, ये हमने already सारा discuss किया है, non-polar, molecular, polar, hydrogen bond and hydrogen bonded. Fine. सो अगेन वी हैव द कॉन्स्टिट्यूएंट पार्टिकल्स. यहाँ सारे केसेस में मॉलिक्यूल्स ही होंगे. आयोनिक में आयंस होंगे, मेटालिक में पॉजिटिव आयंस होंगे जो बेसिकली हमारे मेटल्स होते हैं सराउंडेड बाय इलेक्ट्रॉन्स, और कोवलेंट में भी हमारे नॉन मेटल्स होंगे. फाइन. हियर यू हैव कोवलेंट बॉन्डिंग, मेटलिक, इलेक्ट्रोस्टैटिक आयोनिक में होता है ऑब्वियसली. मेसिंग इट अप अ लिटिल. Okay, so we have then similarly hydrogen bonded होगा. ठीक, in case of hydrogen bonding, and polar dipole dipole interaction non-polar होगा तो simply the dispersion or London forces. And the examples, the properties are also given over here. The conductivity again, यहाँ पे conductors सिर्फ basically हमारे ये है, right? Metallic solids जो होते हैं they are conductors. Fine. Covalent में हमने देखा again there they can be graphite which is an exception and it's a conductor because of its structure, layered structure. ठीक है, और जो hexagonal geometry है. And there's also given the melting point. ठीक, you can just go through the table. Moving on, अब हम कुछ different करेंगे. I think जो हम अब तक कर रहे थे probably all of us have heard it at one point or the other in chemistry. Now we are going to move on to something new. Now that is crystal lattices and unit cells. Very easy again, just a matter of imagination. So you just have to be here and it's like a story, fine? So the main characteristic of crystalline solid is a regular and repeating pattern of constituent particles. Fine. If the three-dimensional arrangement of constituent particles in a crystal is represented diagrammatically, in which each particle is depicted as a point, the arrangement is called a crystal lattice. Again, हमने सिंस इन डेप्थ वी हैव डिस्कस्ड क्रिस्टलाइन सॉलिड्स क्या होते हैं, अमॉर्फस क्या होते हैं, तो अगर हम क्रिस्टलाइन सॉलिड के जो स्ट्रक्चर है 3D में इफ वी आर ट्राइंग टू डायग्रामेटिकली रिप्रेजेंट इट, तो हर एक पार्टिकल को एक एक पॉइंट से रिप्रेजेंट करेंगे, दैट इज आवर क्रिस्टल लैटिस. So regular three-dimensional arrangement of points in space is called a crystal lattice. A portion of a crystal lattice is shown. You can see. ठीक है, एक portion दिखाया है पूरे 3D इसका. There are only 14 possible three-dimensional lattices. These are called the Bravais lattices. ठीक है. Each point in a lattice is called lattice point or lattice site. जो एक एक हमारे atom को एक particle को represent करेगा. Each point in a crystal lattice represents one constituent particle which may be atom, molecule, group of atom, whatever ion. ठीक है. Lattice points are drawn by straight lines to bring out the geometry of the lattice. Unit cell क्या होता है? It's another term. Unit cell is the smallest portion of a crystal lattice. सबसे छोटा portion है crystal lattice का, उसको हम unit cell बोलते हैं. Which when repeated in different directions generates the entire lattice. So it's a unit cell जिसको periodically repeat करके हमें अपना क्या मिलेगा, अपना पूरा crystal lattice मिलेगा. A unit cell is characterized by its dimensions along the three edges. कैसे देखेंगे, इसका क्या characteristic है? You have A, B, C. ठीक है, यहाँ पे diagrammatically दिखाया हुआ है. They may be or may not be mutually perpendicular. You have angles between the edges alpha, ठीक है, beta and gamma. तो 6 पैरामीटर्स हो गए, लेंथ्स हो गए एजेस के और एंगल्स होंगे. दीज आर शोन over here. Next, we have primitive and centered unit cells. Unit cells can be broadly classified into two categories, primitive and centered unit cells. Primitive unit cells, when constituent particles are present only on the corner positions of a unit cell, उसको primitive cell बोलते हैं. ठीक है, particles सिर्फ corner पे. Center में क्या होगा? When a unit cell contains one or more constituent particles at positions other than the corners, in addition to those at corners. Corners पे तो है ही है. In addition to that कहीं और भी है. It is called a centered unit cell. तो दो किस्म के हमारे पास unit cells है. You have a primitive one, you have a centered one. Centered भी तीन किस्म के हैं, ठीक, क्योंकि हम cubic unit cell ले रहे हैं, तो you have a body centered. Such a unit cell contains one constituent particle at its body center besides the one that are at its corners. Face centered. Face centered में कहाँ होगा? Again, such a unit cell contains one constituent particle present at the center of each face besides the ones that are at its corners. Then end centered, ends पे होगा, is present at the center of any two opposite faces between the ones present at its corners. ठीक, in all there are 7 types of primitive cells. अब हमारे पास कौन से 7 types है? क्यूबिक है, टेट्रागोनल है, ऑर्थोरोम्बिक है, हेक्सागोनल है, रोम्बोहेड्रल, मोनोक्लिनिक एंड ट्राइक्लिनिक. एंड यू हैव टू रिमेंबर द पैरामीटर्स ए बी सी अल्फा बीटा गामा. ठीक है, ऐसे आप अगर इसको एक टैबुलर फॉर्म में लिखेंगे, इट विल बी इजियर फॉर यू टू लर्न इट दैट वेज, बट यू हैव टू लर्न दिस. ठीक है, कुछ एज सच इसमें एक्सप्लेनेटरी रहता नहीं है. Okay, so it's actually given in the NCRT only. The table also. Again, यहाँ पे याद रखना है आपके different types, 7 types के आपके यहाँ पे जो है centered cells हो गए. ठीक, you can have तीन तीन यहाँ पे दिया हुआ है. What possibilities present for every crystal? Say it's a cube, it can be primitive, it can be body centered or face centered. और यहाँ पे आपको याद रखना है, you just have to remember these names. ठीक है, जो आपके यहाँ पे types of lattices है, फिर उनके actual distances. ठीक, उसके बाद ये पूरा टेबल, इसी तरह उनके एंगल्स और उनके एग्जांपल्स, ये आपको याद रखना है. फाइन, ऑलराइट. ब्रेवेस्ट लैटिसेस जो आपके पास 14 पॉसिबल होता है. ठीक है, दिस इज अ प्रिमिटिव वन, सिर्फ कॉर्नर पे होगा, बॉडी सेंटर्ड, बॉडी के सेंटर पे होगा, फेस सेंटर्ड. कितने फेसेस होते हैं क्यूब में? इट्स 6. तो 6 हमारे फेसेस पे होंगे. देन यू हैव अनदर tetragonal, one side different in length to the other. यहाँ पे इन्हें दिया हुआ है. It's not again the cubical one. ठीक, यहाँ पे again orthorhombic वाले में it's just the same. Imagination का बात है. End centered, ये जो opposite faces है, दो opposite faces के centers में, ठीक है, that is end centered. You have body centered and you have face centered. Next up we have monoclinic lattices. हाँ, unequal sides, two faces have angles different from 90 degrees. ठीक, ये हम table से भी याद रख सकते हैं. Next we have number of atoms in a unit cell. We know that any crystal lattice is made up of a very large number of unit cells, and every lattice point is occupied by one constituent particle, atom, molecule or ion. Let us now work out what portion of each particle belongs to a particular unit cell. अब हम देखते हैं कि हम कैसे डिस्ट्रीब्यूट कर रहे हैं, या एक पार्टिकल जो है वो कितने सेल्स के बीच में डिवाइड हो रहा है. डिस्ट्रीब्यूशन देखने वाले हैं. फाइन, we shall consider 3 types of cubic unit cells, and for simplicity assume that the constituent particle is an atom. ठीक, Let's come to primitive one. Primitive में क्या होता है? Only has atoms at its corner. Easy. Each atom at a corner is shared between 8 adjacent unit cells as shown in figure. आपको पता है एक यहाँ पे एक corner पे दिया हुआ है, ठीक है? This atom is at a corner. You can see अगर आप three dimensionally इसको थोड़ा सा visualize करेंगे, then it's actually divided into 8 different cubes, ठीक? At the corner. So 8 तो कॉर्नर्स होते हैं, ठीक? यहाँ पे इन्हें लिखा है 4 unit cells in the same layer and 4 upper or lower layer. Therefore, only 1/8 of an atom or molecular ion actually belongs to a particular unit cell. In case of primitive वाला, ठीक है? Corner पे. A primitive cubic unit cell has been depicted. Each small sphere represents only the center of the particle occupying that position and not its actual size. Such structures are called open structures. You can see over here. ठीक? यहाँ पे the arrangement of particles is easier to follow in open structures. 1.9b में कुछ दिया हुआ है depicts space filling representation of the unit cell with actual particle size. ठीक? In all, since each cubic unit cell has 8 atoms, corner 8 है, ठीक? और एक cubic unit cell में कितने corners होते हैं? 8. 8 atoms at its 8 corners. Total number of atoms in one unit cell. अब हम 8 into 1/8 क्यों कर रहे हैं? एक यूनिट सेल में एक ही एटम क्यों कंसिडर करेंगे? क्योंकि कॉर्नर तो 8 है, उस पे तो 8 एटम्स है, पर क्या वो पूरे-पूरे 8 हैं? नहीं, वो 8 क्यूब्स में डिवाइड है। सो 8 into 1/8 will give you 1 atom. Next we have a body-centered cubic unit cell. A body-centered cubic, you call also this BCC, body-centered cubic unit cell, has an atom at each of its corners and also one atom at its body center. अब हम primitive वाले पे नहीं है, फाइन, हम centered वाले पे जा रहे हैं. You can see over here ओपन स्ट्रक्चर दिया है, फिर स्पेस फिलिंग मॉडल दिया है और फिर प्रोपोर्शंस ऑफ एटम्स एक्चुअली बिलोंगिंग टू इट, है ना? सेंटर वाला तो पूरा सेल बिलोंगिंग है, बट यू कैन सी यहाँ पे इट्स ओनली 1/8 ऑफ अ कॉर्नर एटम. अच्छा, it can be seen that the atom at the body center wholly belongs to the unit cell in which it is present. ये पूरा है इसमें. Thus in a body centered cubic cell, एक तो हमारे 8 corners पे 1/8 of an atom, ये अपना constant हर जगह. This is about the primitive वाले में भी देखा था, but one body centered one atom. What is the total number of unit atoms in a unit cell? It's 2 in case of a body centered one. Coming on to face centered cubic unit cell. A face centered cubic unit cell contains atoms at all the corners. वो तो है ही, center of all the faces of the cubes. ठीक है, अब हर एक face पे भी होगा. It can be seen that each atom located at the face center is shared between two adjacent unit cells and only half of each atom belongs to a unit cell. Very easy. Again imagination. अगर मैं face पे एक cube imagine करें, उसके किसी भी face पे मैंने atom रखा, अगर मैं बहुत सारे cubes को एक साथ मिला रही हूँ तो one atom at a face is shared by two. So only half of that atom at the face center will be depicted. Fine. अब यहाँ पे again open structure, space filling model and the unit cell with portions of atoms actually belonging to it दिया हुआ है in the three structures. ठीक? In a face centered cubic unit cell FCC 8 कॉर्नर पे 8 है into 1/8, ये एक एटम आपका कॉर्नर वाला. उसके बाद स्पेस सेंटर्ड है, कितने फेसेस है? 6. एक फेस पे कितना है? हाफ एटम. 6 into 1.1/2 is 3 and total फेस सेंटर्ड में 4 एटम्स होंगे. इजी. नेक्स्ट, अब हमारे पास है क्लोज पैक्ड स्ट्रक्चर्स. अब हम पैकेजिंग करेंगे, ठीक है? सॉलिड्स में हमें पता है ना क्लोजली एसोसिएटेड होता है मॉलिक्यूल्स. लेट्स पैक द सॉलिड्स नाउ. फाइन. In solids, the constituent particles are close packed, leaving the minimum vacant space. ये तो हमें पहले ही पता है. Let us consider the constituent particles as identical hard spheres and build up a three-dimensional structure in 3 steps. अब हम एक 3D structure बनाएंगे. Fine, are you all ready? And we are taking space for convenience. First is close packing in one dimension. बहुत easy है, एक dimension में, यहाँ नहीं line linear ऐसे बनाया हुआ है, बस इसी को देखो, हो गया close packing in one dimension. Fine. There's only one way of arranging spheres in one-dimensional close-packed structure, that is to arrange them in a row and touching each other. In this arrangement, each sphere is in contact with two of its neighbors. The number of nearest neighbors of a particle is called its coordination number. 1D में देखेंगे, coordination number will be 2. Line में एक atom कितने atom से surrounded है? 1 and 2. Thus, in one-dimensional close-packed, the coordination number is 2. Two dimensions में आए अब. Two dimensional close pack can be generated by stacking the rows of close packs. अब हम ऐसे जो हमने लीनियर यहाँ बनाया ना, इसके ऊपर एक और चढ़ाएंगे, इसके नीचे चढ़ाएंगे. फाइन, गेटिंग मी? तो ऐसे रोज बनाएंगे वन ओवर दी अदर. अब इसको दो तरीकों से किया जा सकता है, या तो वन अबव दी अदर, ऐसा कुछ बिल्कुल सीध में जा रहा है, वर्टिकल सिमेट्री, या फिर फिलिंग द स्पेसेस. लेट्स सी, पहला वाला दिया है The second row may be, I think ये diagram से आपको already समझ आ गया होगा, but still let me just read this for you all. The second row may be placed in contact with the first one such that the spheres of the second row are exactly above those of the first one. बोला मैंने सीधा सीध में जाएंगे. The spheres of the two rows are aligned horizontally as well as vertically. If we call the first row as A, the second row will be exactly the same as the first one, so it will also be A. तो हम ऐसे को क्या कहते हैं? We call it A type of arrangement. हम similar rows को stack कर रहे हैं one over the other, horizontal as well as vertical symmetry. दूसरा वाला देखें. दूसरे वाले में अच्छा, trying to say something about the first one. In this arrangement, each sphere is in contact with four of its neighbors. Thus, the two-dimensional coordination number is 4. अगर हम लेंगे पहले वाले में तो 4 coordination number आएगा. You can see nearest neighbors 4 है. ठीक. अब also, if the centers of these four immediate neighboring spheres are joined, a square is formed. Hence, this packing is called the square closed packing in two dimensions. अब दो तरीके हैं ना closed packing के in 2D. तो एक हो गया हमारा square closed packing जहाँ coordination number 4 होगा by joining the coordination number वाले atoms, neighboring atoms, ठीक, neighboring spheres rather. Next आता है हमारा the second row may be placed above the first one in a staggered manner such that its spheres fit in the depressions of the first row. Again, very diagrammatic, very something that you have to visualize. यहाँ पे देखें, ये मेरा एक लाइन दिया हुआ है. ये जब मैं दूसरा फिल इन कर रही हूँ, मैं इन दो के डिप्रेशन में इसके ऊपर फिल कर रही हूँ. इट्स इन अ स्टैगर्ड मैनर. इट्स नॉट रियली एग्जैक्टली vertical symmetry. There's no vertical symmetry. So if this is A, this is B, this is A, this is B, this and this are similar. They're placed one above the other. But ये जो है ये depressions fill कर रहा है. ठीक है. This is known as, अभी देखेंगे इसको हम क्या बोलते हैं. All right. If the arrangement of spheres in the first row is called A type, the one in the second row is different and may be called B type. When the third is placed in staggered manner, its spheres are aligned with those of the first. जैसे हमने diagram में देखा. Hence, this layer is also of A type. The spheres of similarly placed fourth row will be aligned with those of the second one. Hence, this arrangement is of AB type. Fine. In this arrangement, there is less free space and this packing is more efficient than the square closed packing. जहाँ free space कम होगा, जहाँ packaging ज़्यादा efficiently होगा, वो हमारा that is our hexagonal closed packing. Fine. In this arrangement, there's less free space or packing is rather efficient. Each sphere is in contact with 6 of its neighbors. Unlike square closed packing in 2D. वहाँ पे 4 था. तो वहाँ पे coordination number was 4. Here it is 6. Or the centers of these 6 spheres are at the corners of a regular hexagon. जब हम इन neighboring atoms के centers को join करते हैं, हमें hexagon मिलता है. इसीलिए इसको हम two-dimensional hexagonal closed packing बोलते हैं. This in this layer there are some voids or empty spaces. These are triangular in shape. The triangular voids are of two different types. In one row the apex of the triangle is pointing upwards, next layer downwards. Voids are basically empty spaces. अब ये भी कुछ depressions, कुछ ऐसे spaces रह रहे हैं which are to be filled. Fine, उनको voids बोलते हैं. You can see this is one of the void and this is another one. एक में triangle में apex pointing upwards, एक में downwards. Fine, this is about your face centered your closed packing in 2D. अब आते हैं 3D में closed packing. All real structures are three dimensional. हम क्या देख रहे हैं वो सब 3D है, right? They can be obtained by stacking two dimensional layers one above the other. In the last section, we discussed closed packing in 2D, which can be of two types: square closed and hexagonal. Let's see what types of 3D closed packing can be obtained from these. अब 2D को ही stack करना है one after the other layers में, और हमें क्या मिलेगा? 3D मिलेगा. एक हो गया. अब 2D में भी दो types थे. एक तो स्क्वायर क्लोज पैक था, दूसरा हेक्सागोनल क्लोज पैक था. सिमिलरली हम 3D के भी टाइप्स देखने वाले हैं. थ्री डिमेंशनल क्लोज पैकिंग फ्रॉम टू डिमेंशनल square close pack layers. So again from the diagram you can understand it really well if you just analyze this diagram. ठीक है 3D में तो ये reading it's just for the sake of reading it, but actually you have to visualize things. Fine, so I'll still read it. While placing the second square close pack layer above the first, we follow the same rule that was followed when one row was placed adjacent to the other. The second layer is placed over the first such that the spheres of the upper layer are exactly above those of the first layer. In this arrangement, spheres of both the layers are perfectly aligned horizontally as well as vertically. Similarly, we may place more layers one above the other. If the arrangement of spheres in the first layer is called A, then all the layers will have the same arrangement. Again, A type pattern. Fine. This generates a simple cubic lattice, fine, and its unit cell is the primitive cubic unit cell. Coming to three-dimensional close packing from 2D hexagonal close pack layers. 3D close pack structure can be generated by placing layers one over the other. ठीक, अब इसमें हमारे पास we have ways to place second layer over the first one. ठीक, इन्हें पहला वाला दिया है, again just visualize, नीचे से थोड़ा lightish pinkish shade दिया हुआ है and ऊपर दूसरा layer is by red color. Let us take a 2D hexagonal close packed layer A, ठीक, and place a similar layer above it so that the spheres of the second layer are placed in the depressions of the first layer. Since the spheres of the two layers are aligned differently, let us call the second layer as B. It can be observed that not all the triangular voids of the first layer are covered by the spheres of the second layer. This gives rise to different arrangements. Whenever a sphere of the second layer is above the void of the first layer, or vice versa, a tetrahedral void is formed. These voids are called tetrahedral voids because a tetrahedron is formed when the centers of these four spheres are joined. They have been marked as T. ठीक है, यहाँ पे इन्हें दिया हुआ है. This is a tetrahedral void. This is a tetrahedral hole. You have four atoms like this. जब हम इनके centers को join करते हैं ना, it's somewhat tetrahedrally बनेगा. Fine. यहाँ पे again, अभी octahedral की बारी आएगी next वाले में. ठीक. At other places, the triangular voids in the second layer are above the triangular voids in the first layer, and the triangular shapes of these do not overlap. ठीक, एक का apex ऊपर होता है, दूसरे का pointing downwards. These voids have been marked as O. Such voids are surrounded by six spheres and are called octahedral voids. ठीक, one such void has been shown separately. यहाँ पे देखेंगे. This is an octahedral void. पहले तो तीन है, उसके ऊपर और तीन है, ट्राइंगल पे ट्राइंगल void आ रहा है, मगर जो ट्राइंगल्स है वो ऑपोजिट है, एक का ऊपर है अपेक्स, दूसरे का नीचे है, तो बीच में व्हाट यू गेटिंग इज दैट octahedral void. यहाँ पे there are some formulas given, very easy and important also. Let the number of closed packed space be n. So number of octahedral voids is n, very formula based, and number of tetrahedral voids is 2n. अब थर्ड लेयर जब डालेंगे सेकंड लेयर पे, ठीक है, 3D बनाना है. अब हम क्या कर सकते हैं, अगेन देयर आर टू पॉसिबिलिटीज कवरिंग द टेट्राहेड्रल वॉइड्स. टेट्राहेड्रल वॉइड पहले ही बने हुए हैं, ठीक है, ऑफ द सेकंड लेयर में बी कवर्ड बाय द स्पेयर्स ऑफ द थर्ड लेयर. इन दिस केस द स्पेयर्स ऑफ द थर्ड लेयर आर एग्जैक्टली अलाइंड विद दोज ऑफ द फर्स्ट. अब क्या समझ आ रहा है आपको, जब हम तीसरा लेयर डाल रहे हैं वो एग्जैक्टली पहले वाले जैसे आ रहा है. इफ यू आर ट्राइंग टू कवर द टेट्राहेड्रल वॉइड्स, दैट्स द पैटर्न ऑफ स्पेयर्स इज रिपीटेड, तो अगेन हमारे पास ए बी पैटर्न आएगा. फाइन, दिस इज हेक्सागोनल क्लोज पैक्ड स्ट्रक्चर. This sort of arrangement of atoms is found in many metals like magnesium and zinc. अब दूसरा क्या पॉसिबिलिटी है, कवरिंग द ऑक्टाहेड्रल वॉइड्स. पहले मैं टेट्राहेड्रल किया, व्हेन यू आर प्लेसिंग द थर्ड लेयर, दूसरे में ऑक्टाहेड्रल. द थर्ड लेयर may be placed above the second layer in a manner such that its spheres cover the octahedral voids. When placed in this manner, the spheres of the third layer are not aligned with those of either the first or the second layer. अगर हम octahedral voids cover करने बैठेंगे तो ना हम पहले layer के साथ जा रहे हैं ना दूसरे, हम एक different arrangement produce करें, and that is C type. Only when the fourth layer is placed, its spheres are aligned with those of the first one. तो हमारे पास आता है ABC type. तो चौथा layer, in case of covering an octahedral void, this is what happens in 3D. This is called a cubic close packed or face centered cubic structure. The copper, silver crystallize in this structure. Both these types of close packing are highly efficient, and 74% space in the crystal is filled. Efficiency दिखा रहे हैं, ठीक? In either of them, each sphere is in contact with 12 spheres. Thus, the coordination number is 12 in either of these two structures. फिर हमारे पास formula of a compound and number of voids filled. अब थोड़ा mathematical aspect है. Earlier in this section, we have learned that when particles are closed, packed, resulting in either CCP or HCP, two types of voids are generated: octahedral or tetrahedral. While the number of octahedral voids in a lattice is equal to the number of close packed particles n, the number of tetrahedral voids generated is twice this number. In ionic solids, the bigger ions, usually anions, form the close packed structure and the smaller ions occupy the voids. ठीक है, ionic solids में क्या होता है, एनायंस जो हैं, बड़े आयंस हैं, वो क्या बनाएंगे, स्ट्रक्चर बनाएंगे, और छोटे आयंस वॉइड्स बनाएंगे. इफ द लैटर आयन इज स्मॉल इनफ देन टेट्राहेड्रल वॉइड्स आर ऑक्यूपाइड. If bigger than octahedral voids, not all octahedral or tetrahedral voids are occupied in a given compound. Not the fraction of octahedral or tetrahedral voids that are occupied depends upon the chemical formula of the compound. ठीक, कुछ एग्जांपल्स दिए हैं, तो जो केमिकल फॉर्मूला होगा उसके बेस पे डिपेंड करता है कि हमारा कितने वॉइड्स बचे हैं और कितनी एफिशिएंसी है. तो अब ये जो एग्जाम्पल्स अगेन बेस्ड अपॉन ऑल ऑफ द थ्योरी दैट वी हैव डन सो फार, ठीक है, किसमें कितने एटम्स लगते हैं और नंबर ऑफ ऑक्टाहेड्रल वॉइड्स टेट्राहेड्रल वॉइड्स कितना होता है, ठीक है, और रेशियोज निकालेंगे फिर आप दो इनके एंड यू विल गेट द आंसर. फाइन, लोकेटिंग टेट्राहेड्रल एंड ऑक्टाहेड्रल वॉइड्स. टेट्राहेड्रल Let us consider unit cell. The unit cell is divided into 8 small cubes. ठीक? Each small cube has atoms at alternate corners. In all, each small cube has 4 atoms. When joined to each other, they make a regular tetrahedron. Thus, there's one tetrahedral void in each small cube and 8 tetrahedral voids in total. Hmm? एक छोटे cube में एक tetrahedral void है. ठीक? Each of the 8 small cubes have one void in one unit cell of CCP. CCP has 4 atoms per unit cell. Thus, the number of tetrahedral voids is twice the number of atoms जो हम already कर चुके हैं. Then locating octahedrals. अब again unit cell consider किया है. Body centers of the cube C is not occupied but it is surrounded by 6 atoms on face centers. If these face centers are joined, an octahedron is generated. Thus, this unit cell has one octahedral void at the body center of the cube. Besides the body center, there's one octahedral void at the center of each of the 12 edges. It is surrounded by 6 atoms, 4 belonging to the same unit cell and 2 belonging to 2 adjacent unit cells. Since each edge of the cube is shared between 4 adjacent unit cells, so is the octahedral void located on it. Only 1/4 of each void belongs to a particular unit cell. एक यूनिट सेल में एक octahedral void का सिर्फ 1/4 है. You don't have to remember all the description. Fine. Then we have packing efficiency, the next topic. In whatever way the constituent particles are packed, there's always some free space in the form of voids. So packing efficiency basically is the percentage of total space filled by the particles. ठीक है, कितना packing है, self explanatory again. Packing efficiency in HCP, CCP structures, इनमें दोनों में you have equally efficient. ठीक है, let us calculate. Again mathematics कराया इन्होंने. Triangle लिया हुआ है ABC, fine. This is the triangle. फिर Pythagoras लगाया हुआ है. ठीक. Hypotenuse square is equal to base square plus perpendicular square. और यहाँ से हमें b small b का value मिला है. Fine, which is this. फिर r is taken to be the radius of the sphere. ठीक. यही b जो है it's equal to 4 times r. ठीक है, एक तो इसके दो, इसका diameter 2 times r, इसका r और इसका r. Fine. ये हम किसका करें? This is for cubic closed packing. जहाँ पे अच्छा 4r is equal to root 2a. You are going to equate the two b's. तो यहाँ से you'll get the value of a which is 2 root 2r. यहाँ rationalization किया है. Fine. We know that each unit cell in CCP structure is effectively 4 spheres. हमें ये पता है total volume of 4 spheres. अब volume wise देखेंगे. Total हमने starting में ही किया. CCP में you have 4 spheres. Total volume will be 4 into volume of 1 spheres. और volume of cube will be side cube. Side हमने निकाला अभी b. This b is already done. Packing efficiency is volume occupied by 4 spheres divided by total volume of the unit cell. Fine. कितना 4 spheres occupy करे divided by कितना cell का already volume है in multiplied by 100. This will give you कि कितने voids हैं या कितना packing efficiency है. Then you have body centered में. अब body पे भी एक है. Fine. There'll be an atom at the center will be in touch with the other atoms to diagonally arranged. यहाँ पे this is if this is at the center. Fine. ये यहाँ पे हमारे पास कॉर्नर्स पे तो होते ही हैं, राइट. अगेन ट्रायंगल लिया हुआ है EFD. You basically have to take your pen and pencil and do this. So I cannot just read this out and सारा घुस जाएगा दिमाग में. I'm not sure about that. But yeah, it's just all about calculations. Again Pythagoras लगाया है, ठीक है. और फिर दूसरा ट्रायंगल भी लिया है. सही. The length of the body diagonal C is equal to 4r. R is the radius of the sphere as all the 3 spheres along the diagonal touch each other. और radius भी फिर उसी तरीके से कितने spheres उस line में आ रहे हैं. फिर again R की value निकाली है. Total number of atoms is 2. ठीक है, corners वाले एक और हमारा body center वाला एक. Fine. और volume हमने ऐसे कर लिया 2 multiplied by volume of 1. ठीक. A cube volume of cube हमारा होता है. Clear. और साइड हमने ऑलरेडी निकाला है. अगेन 68%. Packing efficiency in simple cubic lattice. Atoms are located only on the corners of the cube. The particles touch each other along the edge. Thus, the edge length or side of the cube A and the radius of each particle is related as. ठीक, दो atoms. The volume of the cubic unit cell is A cube, 2r whole cube. ऐसे करेंगे. Again, same formula. Packing efficiency का volume of one atom divided by volume of cubic unit cell. ठीक, and that is into 100 percentage के लिए and you'll get 52.4. We may conclude that CCP HCP have maximum packing efficiency. अब हम लेते हैं involving unit cell dimensions. From the unit cell dimensions possible to calculate the volume of the unit cell. Knowing the density of the metal, we can calculate the mass of the atoms in the unit cell. The determination of the mass of a single atom gives an accurate method of determination of Avogadro's constant. Suppose edge length of a unit cell of a cubic crystal determined by X-ray diffraction is A, D the density of the solid substance, and M is the molar mass. In case of cubic crystal, volume we know is side cube. Mass कितना होगा? Number of atoms multiplied by number of mass of each atom. Number of atoms is given by Z, or small m will give you mass of each atom. Here Z, अच्छा. Mass of an atom present in the unit cell in terms of molar mass and Avogadro's number. कुछ constants के terms में लेंगे इसको. तो density कैसे लिखेंगे? Mass by volume. What is the mass? Z into m. Small m is molar mass divided by Avogadro's number. So density का ये formula बाहर आ जाता है. Remember, the density of the unit cell is the same as the density of the substance. ठीक? Density of the solid can always be determined by other methods. So out of the 5 parameters, if any 4 are known, we can determine the fifth one. यहाँ पे formula based question. Fine. Again, volume is mass per unit density. Volume हमें पता है. Fine. And number of unit cells निकाला है. You are going to solve these. Fine. Next we have imperfections in solids. अब हम defects वगैरह देखेंगे. Very easy. Although crystalline solids have short range as well as long range order in the arrangement of their constituent particles, yet crystals are not perfect. ठीक है, हर एक में कुछ ना कुछ impurity, कुछ ना कुछ imperfection आता है. Usually a solid consists of an aggregate of large number of small crystals. These small crystals have defects in them. This happens when crystallization process occurs at fast or moderate rate. Single crystals are formed when the process of crystallization occurs at extremely slow rate. Even these crystals are not free of defects. The defects are basically irregularities in the arrangement of constituent पार्टिकल्स. मतलब जो पार्टिकल्स है उनके अरेंजमेंट में इरेगुलरिटी है, उसी को डिफेक्ट कहेंगे. ब्रॉडली स्पीकिंग, द डिफेक्ट्स आर ऑफ टू टाइप्स, नेमली पॉइंट डिफेक्ट्स एंड लाइन डिफेक्ट्स. Point defects are the irregularities or deviations from ideal arrangement around a point or an atom in a crystalline substance, whereas the line defects are the irregularities or deviations from ideal arrangement in entire rows of lattice points. Again, term आपको खुद ही बता रहे. पॉइंट डिफेक्ट मतलब डिविएशन है एक पॉइंट में, एक एटम में. लाइन डिफेक्ट मतलब पूरी पूरी लाइन में, पूरे पूरे रो में, लैटिस में गड़बड़ है. दीज irregularities आर कॉल्ड क्रिस्टल डिफेक्ट्स. फाइन. We shall confine our discussion to point defects only. अब हमें देखना है, they can be again impurity defects, stoichiometric and non-stoichiometric defects. पहला यहाँ पे दिया हुआ है स्टाइक्योमेट्रिक डिफेक्ट. दीज आर द पॉइंट डिफेक्ट्स दैट डू नॉट डिस्टर्ब द स्टाइक्योमेट्री, यानी आपका स्टाइक्योमेट्री विल रिमेन द सेम. दे आर कॉल्ड इंट्रिंसिक और थर्मोडायनामिक डिफेक्ट्स. बेसिकली इस स्टाइक्योमेट्रिक के हमारे पास और दो टाइप्स है. फाइन. वैकेंसी डिफेक्ट एंड इंटरस्टिशियल डिफेक्ट. इसमें क्या हो रहा है? स्टाइक्योमेट्री हमारा सेम रह रहा है. वैकेंसी क्या होगा? वेरी इजी. खाली खाली जगह, void present. Fine. When some of the lattices sites are vacant, crystal is said to have vacancy defect. यहाँ पे very easy. ये तो मतलब डायग्राम ही समझा रही है. This results in decrease in density of the substance. जब खाली जगह है density कम हो जाता है. Again, interstitial defect. Interstitial क्या होता है? एक some constituent particle occupy an interstitial site. It is said to have interstitial defect. इससे density बढ़ जाती है क्योंकि molecules come closer. ठीक है, molecule अपनी जगह से हटके interstitial site पे आ जाता है, इसको interstitial कहते हैं. Vacancy and interstitial are explained above, can be shown by non-ionic solids. Ionic solids must always maintain electrical neutrality. Huh? Rather than simple vacancy or interstitial defects, they show these defects as फ्रेंकल एंड शॉटकी डिफेक्ट्स. अगर हम आयनिक सॉलिड्स की बात करें, वहां पे हमारे पास सीधा वैकेंसी या इंटरस्टिशियल डिफेक्ट नहीं आता. वहां पे आपको इलेक्ट्रिकल न्यूट्रलिटी मेंटेन करना पड़ता है. फाइन. वहां पे हम डेंसिटी के टर्म्स में बात नहीं करते, हम वहां इलेक्ट्रिसिटी के टर्म्स में बात करते हैं. यू हैव अ फ्रेंकल डिफेक्ट एंड यू हैव शॉटकी डिफेक्ट इन केस ऑफ आयनिक सॉलिड. फ्रेंकल में क्या है? दिस डिफेक्ट इज शोन बाय आयनिक सॉलिड. Smaller ion cation is dislocated from its normal site to an interstitial site. It creates a vacancy defect in its neutral site and an interstitial defect at its new location. जहां से गया उधर vacancy defect, जहां गया उधर interstitial defect create कर लिया. Frenkel is also called dislocation effect. It does not change the density of the solid. Frenkel defect is shown by ionic substance in which there is a large difference in the size of ions. ठीक है, cation and anion में बहुत फर्क है. Schottky में क्या है? Vacancy defect है ionic solids पे. Basically, in order to maintain electrical neutrality, the number of missing cations and anions are equal. इलेक्ट्रिकल न्यूट्रलिटी मेंटेन करना है आयनिक सॉलिड में. अगर शॉर्ट भी हो रहा है, अगर वैकेंसी भी आ रही है, फिर भी जितना पॉजिटिव गया है उतना एनायन को भी गायब करेंगे ताकि न्यूट्रल रहे. फाइन. जितना पॉजिटिव उतना नेगेटिव. Like simple vacancy defect, Schottky defect also decreases the density of the substance. Number of such defects in ionic solids is quite significant. For example, in NaCl there are approximately 10 raised power 6 Schottky pairs. ठीक? Per centimeter cube at room temperature. Thus, there's one Schottky defect per this calculation. It is shown by ionic substance in which size the cation and anion are of almost similar sizes. ठीक, क्योंकि डेंसिटी पे भी फर्क नहीं पड़ता. For example, NaCl, KCl, CSCl, AgBr, density of course decreases in such cases, but हमें electrically सबको neutral रखना है. Fine. यहाँ पे AgBr जो है shows both Frenkel as well as Schottky defects. अब impurity defects खुद ही बोल रहा है कि impurity आ रही है. अगर molten NaCl है containing a little amount of strontium chloride crystallized, some of the sites of sodium ions are occupied by Sr2 positive. अगर Na plus को Sr2 plus से replace किया, इसका मतलब दो Na plus को एक ही Sr plus replace कर सकता है, isn't it? Because electrical neutrality. So it occupies the site of one ion and the other site remains vacant. अब एक आयन की जगह तो स्ट्रॉन्टियम आ गया, दो की जगह इनफैक्ट एक स्ट्रॉन्टियम आया, यानी एक जगह जो है खाली रह जाएगा. The cationic vacancies thus produced are equal in number to that of the Sr2 plus ions. जितने Sr2 plus उतने ही cationic vacancies. Another similar example is a solid solution of CdCl2 and AgCl. अब आते हैं नॉन स्टाइक्योमेट्रिक पे. वेरी इजी. नॉन स्टाइक्योमेट्रिक कहाँ आएगा? जहाँ स्टाइक्योमेट्री डिस्टर्ब हो जाएगी. However, a large number of non-stoichiometric inorganic solids are known which contain the constituent elements in non-stoichiometric ratio due to defects in their crystal structures. These defects are of two types. Again, metal excess defect हो गया, metal deficiency हो गया. Metal excess में मतलब anionic vacancies. इसका मतलब cation ज्यादा हो गए, metal ज्यादा हो गया, यानी anions कम हो गए. Alkali halides like NaCl and KCl show this type of defect. When crystals of NaCl are heated in an atmosphere of sodium vapor, sodium atoms are deposited on the surface of the crystal. The Cl negative ions diffuse to the surface of the crystal combine with sodium to give NaCl. जब anion बाहर आ गया, loss of electron by sodium to form Na positive, electron जो release हो गया, will diffuse into the crystal and occupy anionic sites. As a result, crystal now has an excess of sodium. ठीक है, क्योंकि क्लोरीन तो बाहर आ गया, इलेक्ट्रॉन हालांकि वहीं रह गया. The anionic sites occupied by unpaired electrons are called F centers. Okay, for Benzenter center, for the color center. They impart yellow color to the crystals of NaCl. The color results by excitation of these electrons. जहाँ electron देखा वहाँ excite होगा और वहाँ color आएगा when they absorb energy from the visible light falling on the crystal. Similarly, excess of lithium makes LiCl crystals pink and excess of potassium makes KCl crystals violet or lilac. Fine. फाइन. मेटल एक्सेस ड्यू टू द प्रेजेंस ऑफ एक्स्ट्रा केटायंस. ठीक है, जरूरी नहीं है कि एनायन जाएगा, इसका मतलब कभी कभी केटायन भी ज्यादा हो सकता है. जिंक ऑक्साइड in white in color room temperature, on heating it loses oxygen and turns yellow. See, now there's excess of zinc in the crystal and its formula becomes Zn1 plus XO. See, excess Zn plus 2 ions move to interstitial sites and electrons to neighboring interstitial sites. A metal deficiency में many solids which are difficult to prepare in the stoichiometric composition and contain less amount of the metal as compared to the stoichiometric proportion. Proportion से कम metal है इनमें. ऐसे भी solids होते हैं. जहाँ अगर आप 0.93 0.96 Fe का क्या मतलब है, यानी पूरा iron atom नहीं है. A typical example of this is FeO, which is mostly found with a composition of this. It may actually range from this to this. In crystals of FeO, some Fe2 plus cations are missing, and the loss of positive charge is made up by the presence of required number of Fe plus 3 ions. अब electrical properties है solids के. Solids exhibit an amazing range of electrical conductivities extending over 27 orders of magnitude, ranging from this to this. ठीक, solids can be classified into three types on the basis of their conductivities. ये हम पहले भी कर चुके हैं शायद. Conductors, solids with conductivities ranging between 10 raised power 4 to 10 raised power 7. ठीक, इनको conductors कहते हैं. Metals have conductivities in the order 10 raised power 7 per ohm per meter, and they're good conductors. तो 4 से 7 तक याद रखेंगे. ठीक, 4 से 7 तक हमारे पास आते हैं कंडक्टर्स. इंसुलेटर्स में these are solids with very low conductivities, -20, -10. Semiconductors बीच में आएंगे, -6 to 4. Fine. Conduction of electricity. Conductor may conduct electricity through movement of electrons or ions. Metallic conductors belong to the former category and electrolytes to the latter. Fine. या तो movement होगी electrons की या ions की. Metals conduct electricity in solid as well as molten state. Conductivity of metals depends upon the number of valence electrons available per atom. जितने ज़्यादा free electrons उतनी ज़्यादा conductivity. The atomic orbitals of metal atoms form molecular orbitals which are so close in energy to each other as to form a band. If this band is partially filled or it overlaps with a higher energy unoccupied conduction band, then electrons can flow easily under an applied electric field and the metal shows conductivity. ठीक है, अब इसने in terms of atomic orbitals बोला है, metal atoms में जो molecular orbitals बनाते हैं वो इतने close होते हैं energy में कि वो bands बनाते हैं, ठीक है। और फिर हम देख सकते हैं कि bands में आपस में conduction भी हो सकता है। If the gap between filled valence band and the next higher unoccupied band, which is the conduction band, ये आप semiconductors में भी पढ़ते हैं, is large, electrons cannot jump to it क्योंकि distance बहुत ज़्यादा and such a substance is very small conductivity. So this is basically the theory behind conduction. अब semiconductors का भी यही है, ये आप physics में you discuss this in a very good manner. In case of semiconductors, the gap between the valence band and conduction band is small. Therefore, some electrons may jump to conduction band and show some conductivity. Electrical conductivity of semiconductors increases with rise in temperature since more electrons can jump to the conduction band. Substances like silicon and germanium show this type of behavior and are called intrinsic semiconductors. ठीक, the conductivity of these intrinsic semiconductors is too low to be of practical use. उतना होता नहीं है. Their conductivity is increased by adding an appropriate amount of suitable impurity. और इस प्रोसेस को हम क्या बोलते हैं जिसमें हम सेमीकंडक्टर में इम्प्योरिटी डालते हैं, वी कॉल इट डोपिंग. और डोपिंग से क्या होता है, हमारी कंडक्टिविटी बढ़ती है सेमीकंडक्टर की ऑफ प्रैक्टिकल यूज. Doping can be done with an impurity which is electron rich or electron deficient as compared to the intrinsic semiconductor silicon or germanium. Such impurities introduce electronic defects in them. Obviously, जब impurity आएगा तो defect भी आएगा, but this is something we do to increase the conductivity. Electron rich impurities, again, silicon and germanium belong to group 14 of the periodic table, have 4 valence electrons each. In their crystals, each atom forms 4 covalent bonds with its neighbors. When doped with a group 15 element like phosphorus or arsenic, इसमें 5 valence electrons होंगे. They occupy some of the lattice sites in silicon or germanium crystal. 4 out of 5 electrons are used in the formation of 4 covalent bonds. 4 ने तो covalent bond बना लिया, वो बाकी atoms के साथ mix up हो गया, लेकिन था ये ग्रुप 15 का, एक इलेक्ट्रॉन रह जाएगा. द फिफ्थ इलेक्ट्रॉन इज एक्स्ट्रा एंड बिकम्स डीलोकलाइज्ड. और जब भी इलेक्ट्रॉन्स डीलोकलाइज होंगे दे इंक्रीज द कंडक्टिविटी डोप्ड सिलिकॉन. फाइन. Here, the increase in conductivity is due to the negatively charged electron. Hence, silicon doped with electron-rich impurity is called N-type semiconductor. Negatively charged electron से किया तो N-type semiconductor. अब electron deficit impurities देखेंगे. सिलिकॉन और जर्मेनियम कैन ऑल्सो बी डोप्ड विद ग्रुप 13 क्योंकि सिलिकॉन जर्मेनियम ग्रुप 14 के हैं. 15 के साथ किया तो इलेक्ट्रॉन रिच इम्प्योरिटी, 13 के साथ किया तो इलेक्ट्रॉन डेफिसिट इम्प्योरिटीज जैसे बोरॉन, एल्यूमिनियम और गैलियम which contain only 3 valence electrons. Fine. The place where the fourth valence electron is missing is called electron hole or electron vacancy. An electron from a neighboring atom can come and fill the electron hole, but in doing so it would leave an electron hole at its original position. If it happens, it would appear as if the electron hole has moved in the direction opposite to that of the electron that filled it. Under the influence of electric field, electrons would move towards the positively charged plate through electronic holes. अब electronic hole again it will create a way for the electrons to move for their mobility. ठीक है, वो ट्राई करेंगे कवर करना किसको, डेफिसिट को, और इवेंचुअली इससे क्या होगा, इलेक्ट्रॉन्स विल स्टार्ट मूविंग, बट इट वुड अपीयर एज इफ इलेक्ट्रॉन होल्स आर पॉजिटिवली चार्ज एंड आर मूविंग टुवर्ड्स नेगेटिवली चार्ज. दिस टाइप ऑफ सेमीकंडक्टर इज कॉल्ड पी टाइप सेमीकंडक्टर क्योंकि हम पॉजिटिव चार्ज क्रिएट करें. दिस इज अ मोबाइल इलेक्ट्रॉन given over here, positive hole. All right. Application of n-type and p-type semiconductors. Various combinations. Again, I told you physics may you'll do it in a better way, I'm sure. But you just just so you know things, chemistry maybe hai. Various combinations of n-type and p-type semiconductors are used for making electronic components. Diode is a combination of n-type and p-type semiconductors and is used as a rectifier. ठीक है, diode क्या है, basically n-type p-type को combine किया. Transistors are made by sandwiching a layer of one type of semiconductor between two layers of the other type of semiconductor. Right? So this is another. अब सेम है ट्रांजिस्टर्स में भी क्या करें, हम सैंडविच करें एक टाइप का सेमीकंडक्टर बीच में और उसके ऊपर नीचे डिफरेंट टाइप ऑफ सेमी conductor. Find NP and PNP type of transistors are used to detect or amplify radio or audio signals. The solar cell is an efficient photodiode used for conversion of light energy into electrical energy. अब है हमारे पास germanium and silicon are group 14 elements and therefore have a characteristic valence of 4 and form 4 bonds as in diamond. ठीक, कार्बन में बनते हैं 4 बॉन्ड टेट्रावैलेंट. A large variety of solid state materials have been prepared by combination of group 13 and 15 or 12 and 16 to simulate average valence of 4 as in GE or SI. समझ आई बात? 13 15 को ले लो, 12 16 को ले लो, एवरेज क्या आएगा? 14 आएगा. Typical compounds of group 13 15 are INSP, ALP, and GAAS. Gallium arsenide semiconductors have very fast response and have revolutionized in the design of semiconductor devices. हम basically betterment develop कर रहे हैं same type of semiconductor by using various materials. ठीक, इसी तरह 12 to 16 group के भी ऐसे compounds हैं. In these compounds the bonds are not perfectly covalent and the ionic character depends on the electronegativities of the two elements. It is interesting to learn the transition metal oxides show marked difference in electrical properties. ठीक है, these and these behave like metals. Rhenium oxide is like metallic copper in its conductivity and appearance. Certain other oxides like vanadium के oxides दिए हैं, titanium का oxide show metallic or insulating properties depending on the temperature. अब है magnetic properties हमारे पास. Every substance has some magnetic property associated with it. The origin of these properties lies in the electrons. Fine. The origin of these properties lies in the electrons. Each electron in an atom behaves like a tiny magnet. Its magnetic moment originates from two types of motions: its orbital motion around the nucleus and its spin around its own axis. Electron, being a charged particle and undergoing these motions, can be considered as a small loop of current which possesses a magnetic moment. हमने देखा इलेक्ट्रॉन जब प्रोटॉन्स के इर्द गिर्द घूम रहा होता है तो हम कंसिडर कर सकते हैं कि इलेक्ट्रॉन बेसिकली क्या है, एक magnetic moment create कर रहा है. Thus each electron has a permanent spin and an orbital magnetic moment associated with it. और इसका magnitude भी यहाँ पे दिया हुआ है which is also known as the Bohr magnitude. ठीक है, magnetic moment का जो magnitude है that is Bohr magnitude और इसका value यहाँ दिया है, very important. On the basis of their magnetic properties, substances can be classified into 5 categories. Fine. We have paramagnetic, diamagnetic, ferromagnetic, and antiferromagnetic and ferrimagnetic. ठीक है, paramagnetism basically weakly attracted by a magnetic field. They are magnetized in the magnetic field in the same direction. They lose their magnetism in the absence of magnetic field. Paramagnetism is due to the presence of one or more unpaired electrons which are attracted by the magnetic field. तो यहाँ पे examples दिए हैं of such substance. Diamagnetism weakly repelled by a magnetic field, जैसे water, NaCl, benzene. Examples of such substances, they're weakly magnetized, ठीक है, in the opposite direction, इसलिए इनका सबसे weakest power होता है. Diamagnetism, उन इसमें क्या होता है, बेसिकली सारे इलेक्ट्रॉन्स पेयर्ड होते हैं. जब कोई अनपेयर्ड इलेक्ट्रॉन्स नहीं हुए तो इसकी वजह से मैग्नेटिक फील्ड वाज नॉट पॉसिबल. फाइन. Pairing of electrons will cancel their magnetic moments. Ferromagnetism, a few substances like iron, cobalt, nickel, gadolinium, CrO2 attracted very strongly by a magnetic field. और ऐसे substances को हम ferromagnetic बोलते हैं जो बहुत strongly attract होते हैं. Fine. Besides strong attractions, they can be permanently magnetized. ठीक? In solid state, the metal ions of ferromagnetic substances are grouped together into small regions called domains. So, इसमें domain theory will explain the magnetism. Each domain acts as a tiny magnet. In an unmagnetized piece of a ferromagnetic substance, domains are randomly oriented. लेकिन जब हम उसको electric या magnetic field में डालते हैं, domains एक direction में align हो जाते हैं, इसीलिए बहुत ज़्यादा strong magnetic effect जो है produce होता है. That is what it is written over. This ordering of domains persists even when the magnetic field is removed. ठीक है, उसके बाद भी there will be some amount of magnetism left. इसीलिए हम इसको permanent magnet में convert करते हैं. Antiferromagnetism is now substances like MnO showing antiferromagnetism have domain structure similar to ferromagnetic substance, but their domains are oppositely oriented and cancel out each other's magnetic moment. ठीक, इसमें भी वही है, स्ट्रक्चर सिमिलर है, डोमेन्स है, बट दे आर ऑपोजिटली ओरिएंटेड. उसको एंटी फेरोमैग्नेटिज्म बोलते हैं. फेरीमैग्नेटिज्म क्या है? व्हेन द मैग्नेटिक मोमेंट्स ऑफ द डोमेन्स इन द सब्सटेंस आर लाइंड इन पैरेलल एंड एंटी पैरेलल डायरेक्शंस इन अनइक्वल नंबर्स. यानी कुछ पैरेलल है, कुछ एंटी पैरेलल है, सारे ऑपोजिट नहीं है या सारे एक डायरेक्शन में नहीं है. इसको फेरीमैग्नेटिज्म बोलते हैं. दे आर वीकली अट्रैक्टेड एज कंपेयर टू फेरोमैग्नेटिक, जैसे मैग्नेटाइट एंड फेराइट्स. ठीक, मैग्नेटाइट्स एंड फेराइट्स. and Z and Fe2O4 are examples of such substance. These substances also lose ferrimagnetism on heating and become paramagnetic. Fine. यहाँ पे कुछ schematic representation है. I think we are done with the lesson. More of a visualization. I hope the lecture was, I think, even if it was a little helpful to you, um, I just hope you were able to grab anything. And thank you so much for watching. I'll see you in my next one.